So this is G485 homework booklet question 11. Starting off being asked for definition of the electromotive force, so a bit of straightforward G482 synoptic work there, energy transferred from other form to electrical energy per unit charge. And defining magnetic flux, so a G485 definition, simply the product of the flux density in the area perpendicular to that flux. We've got a picture of a simple transformer, an AC supply, we've got some turns, number on the primary, and we've got some turns and number on the secondary, we've got an output, and the primary coil is connected to an alternating voltage supply. Explain how the EMF is induced in the secondary coil. The key here is that EMF is rate of change of flux linkage, so I've got to really demonstrate how I'm getting a changing flux linkage in that secondary. So changing flux is produced in the primary by that AC supply, so we get a changing magnetic field here because of the changing AC supply in that coil. That iron core then means that that flux is linked to and ends up going through that secondary coil, and then we're done. Simple third point, that changing flux in the secondary coil inducing the EMF. So changing flux in the primary from the AC supply, the iron core links that flux to the secondary, and the changing flux in the secondary induces the EMF. Ask you to simply state how you could change the transformer to increase the maximum EMF induced in the secondary. The most obvious thing to do is to simply think in terms of having more turns in the secondary, because that will increase my rate of change of flux linkage for the same rate of change of flux. You can also do it by having fewer turns on the primary. And then we get into some numerical examples. We've got a transformer with that number of turns in the primary, 230 volt main supply. The EMF across the output is 120. Assume the transformer is 100% efficient. Calculate the number of turns in the secondary. Well, remember the key with these basic calculations is that the ratio of the turns is the same as the ratio of the PD. So number in the secondary divided by the number in the primary, 4,200, is equal to the voltage in the secondary, 12, divided by the voltage of the primary, 230, and that works out as 219 turns. The transformer output terminals are connected to a lamp using leads that got a total resistance of 0.35 ohms. The PD across the lamp is 18.5 volts. And we're asked to calculate the current in the leads connected to the wire. This again is G482 synoptic work. G482 synoptic work tends to come in G485. G481 tends to come in G484. And we've got here that we know the PD in the wires. We've got to be careful here. We've got 12 volts EMF from the secondary, and the PD across the lamp is 11.8 volts. So the PD in the wires is 0.2 volts. Then it's a simple V equals IR, rearranged I as V upon R. 0.2 volts divided by that known resistance gives me that current. And the power dissipated in the lead, doing P equals IV, the current we've just worked out, and the V, again, the PD across the leads. It's important here, the key thing here really is to getting the right PD, spotting that that's that 0.2 volts. And that gives you 0.11 watts. That was G485 homework booklet question 11.